Hello everyone, this is lecture 7 of course PE 500. In this lecture, we will cover Laplace transforms, and the Laplace transform is a powerful mathematical tool that converts differential equations from the time domain to the frequency domain, or called S domain, and it simplifies solving linear differential equations by turning them into algebraic equations. So when Laplace transform converts that from the differential equation in the time domain to the frequency domain into algebraic equation, then we can solve this algebraic equation and transform it back in the time domain so that we can get the required function. As definition for a real valued function f of t defined for t more than or equal 0, the Laplace transform is given by Laplace of f of t equals f of s, and here as a notation we convert from lowercase to uppercase, here f in lowercase and here f in uppercase, and we are converting from the time domain to the s domain, and this will equal the integration from 0 to infinity, and we will multiply any function here by the exponential of negative st. We will integrate that to get the corresponding Laplace transform. F of t again is a function in the time domain, and f of s is a transformed function in the s domain, and s here is a complex variable representing the frequency or damping. So let's assume that we have a function t, for example f of t equals t, and we need to convert it to the s domain or apply Laplace transform. Then simply we will integrate it from 0 to infinity and multiply this function, which is t by e, or the exponential of negative st. We will integrate that to get the corresponding Laplace transform. And there are many advantages of using Laplace transform. First, initial value problems made easier because we are directly incorporate initial conditions into the solution. Also, we handle discontinuous inputs gracefully, such as step functions, impulse responses, and piecewise forcing functions. Third, they are used in feedback and control systems as they are essential in the modeling process. For example, artificial pacemakers, insulin pump dynamics, and prosthetic limb control systems. And we use Laplace transform in bioengineering as they simplify the analysis of initial value problems, or in short IVP, especially with discontinuous impulse inputs, and they are used in modeling biological control systems such as pacemaker dynamics, neural response to stimuli, and feedback mechanisms in physiological regulation. So now you have the option whether you are solving the differential equation using the traditional approach, and we covered that in the previous lectures, or you can solve it using Laplace, and both of the ways should lead to similar responses or similar outputs. So again, there's our definition of the Laplace transform. We are multiplying any function by the exponential and integrating it from 0 to infinity. So now, what about if we need the Laplace transform of f of t equals 1? Then simply take the function f of t equals 1 and multiply it by the exponential and then integrate it from 0 to infinity. So the integration of this will be the exponential of negative st divided by negative s, because here we are integrating with respect to t, so s here will be a constant. Now we got the output, we need to substitute by infinity, so e raised to negative s multiplied by infinity, this will give 0 minus the exponential of negative s multiplied by 0, and this will lead to 1. So negative 1 in the numerator and negative s in the denominator. So it will lead to 1 over s. So Laplace transform of 1 will be 1 over s. So now you understand how to apply Laplace transform using the definition. What about if we have a polynomial or a long function such as sine plus cosine plus t square plus t cubic and so on? So should we take each part and apply Laplace transform on each of them? If you are required to apply the definition and follow step by step, then you will need to do that. But if you are inside or solving a big problem and taking Laplace as a part of it, then we can simply use Laplace transform tables. And there are many Laplace transform tables on the internet. You can find one of them and use it, as they will give you a shortcut so you don't have to integrate every time every part of the equation. So simply in that table you will find that Laplace transform of 1 is 1 over s. Other than that, you will need to integrate a step by step to find the solution. So these are common Laplace transforms. If we have e raised to the power of n, the corresponding Laplace transform will be the factorial of n over s raised to the power n plus 1. So take n here, increment 1, and put it in the denominator as a power of s. And then take that n, put here in the factorial. What about the exponential? Exponential of at will be 1 over s plus a. And notice that if it's plus here, it will be negative here. And if it's negative here, it will be plus here. So we are reversing the addition into subtraction, or plus into minus and minus to plus. What about if we have t multiplied by the exponential? Simply, if you notice from here that t raises the power or increments the power, and exponential adds a factor. So we will combine both of them here. E individually will raise to the power of 2 because it's here power to 1, and factorial of 1 is 1, so you will find here 2 and 1. And the exponential plus a will be negative a, and the negative a will be plus a, so this will be the result. Sine at will be a over s square plus a square. Cosine at will be s square over s square plus a square. And combining the exponential and sine, simply we will get that sine, but here we are using b, so it will be b over something square plus b square, and that, because you are using exponential, will add a factor. So plus a will be negative a, and negative a will be plus a. You don't have to memorize all of them. You can bring the table and use it. Once you find a sine, you can substitute. Once you find a cosine, you can substitute. But I'm trying to making it easier for you to remember. These are also the second part of the common Laplace transforms, and there are many more. And here the exponential multiplied by the cosine. So here every s is added to a factor. So it's s minus plus a over s minus plus a squared plus b squared. And the Laplace transform of the first derivative of f of t will be s multiplied by f of s minus f of naught. And f of naught here is the output of substituting by 0 in the original function. And the Laplace transform of the second derivative is s squared multiplied by f of s minus s multiplied by f of naught minus f bar, or the first derivative, and substitute by 0. So if you notice here, there is a pattern, because if I asked you what's the Laplace transform of the third derivative, simply you start by s raised to the power equal to the order here. So s raised to the power of 3 multiplied by f of s. Then each coming f here will be substituted by 0, starting from f naught and incrementing the derivative 1 by 1. And for s, you are decrementing s 1 by 1. How? Simply, we will decrement s until it disappears, or become s to the power of 0, which is 1. So minus s squared minus s raised to the power of 1 minus s raised to the power of 0. And this will be the last part. Then we will start here, multiply by f of naught, then multiply by the first derivative of f of naught, then f second derivative of naught. So you are increasing the derivatives and decreasing the power of s, and combining both of them with negative signs in front of each. But the first one will be special because here f of s. So now you know the pattern. Start by s raised to the power equal to the order multiplied by f of s, and then subtract any upcoming factor or part in the equation. Decrement the power of s and increment the derivatives. Start from f of naught and one by one increase the derivative. To ensure that you are correct, this derivative should be less than this derivative by 1. The second one is called drag delta, or impulse input or sudden input. Its Laplace transform will be 1, and the unit function or the step function or Heaviside step function, its Laplace will be 1 over s. The same, the Laplace of 1 is also 1 over s. So the situation here is very simple. You will find a function f of t, and then using the table, you can find the corresponding Laplace transform. But you may find complex or combined functions, and hence you need to learn different properties, such as linearity. So linearity here means that Laplace transform allows combining multiple functions easily. If you have this function and you need to apply Laplace transform simply because there is plus or minus here, then you can take each of them and apply Laplace individually. So there is a constant will remain, f of t will become f of s, g of t will become g of s, and the constant remains the same. We mentioned the first derivative and the second derivative, and we know the pattern in case you have the third derivative or fourth derivative. Also, there is a common property called time delay or shift theorem. And here, if you have a function f of t minus or plus a multiplied by the unit step with the same factor t minus a, then the corresponding Laplace transform will be the exponential of negative as multiplied by f of s. So here we say that this unit step delayed the response. For example, if you found f of t and a here is 0 multiplied by the unit step, then by finding the unit step and that both of them are equal, then it should be the time delay, and in this case you will apply the time delay or shift theorem. Also, if you found f of t minus 2 u t minus 2, in this case you will apply the same theorem. So try to find the unit step. If you found it, then it should be the time delay theorem. Also, the multiplication by the exponential. If you have a function multiplied by the exponential, then the Laplace transform will be f of s minus a. If you remember from a while, we mentioned that if you have exponential multiplied by something like here or like here or like here, then we are using the same f of s but subtracting or adding according to the sign here by the factor a. If you have convolution, then you can simply convert it to Laplace transform by multiplication. Also scaling, if you have a function a as a constant more than 0 multiplied by t, then the corresponding Laplace transform will be 1 over a multiplied by f of s over a. Also differentiation, if you have a function of t multiplied by t, the Laplace transform will be negative the first derivative of f of s, and this will help compute moments and expected values in stochastic biological models. And for integration, if you have integration from 0 to t, then the corresponding Laplace transform will be 1 over s multiplied by f of s. Also, we have initial value theorem and final value theorem. If you have a limit f of t tends to 0, so the corresponding Laplace transform will be s multiplied by f of s, and substitute for every s by infinity. And the opposite, final value theorem, a function f of t tends to infinity, so the corresponding Laplace will be s multiplied by f of s, and s will be 0. So 0 will be infinity, and infinity will be 0. Also, you don't need to memorize all of them, but you need to get familiar with each rule, as you will find many of them during solving the different problems. For each property or each theorem here, there is a derivation, and we are not going to cover these derivations here. And if you need to look on each derivation, you can visit these websites. Now we have covered different Laplace transformations and different properties, and to get familiar with each of them, let's go to some examples. We have an example, f of t equals to t multiplied by the exponential of negative 2t. First, check the table. If there is a pattern in the table, then you can use the corresponding Laplace transform. Otherwise, you can use different techniques first to make it looks like the pattern, and then use the corresponding Laplace transform. So if you notice here, this function is similar to that function. Then simply we will use the corresponding Laplace transform. We have negative 2, and we mentioned that negative a will be positive a. So the final value will be 1 over s plus 2 squared, because negative will be converted to positive. A second example, we have exponential multiplied by sine. And if you look carefully, you will find that this one is similar to that function. We need the values of a and b. A here is 2, and the negative will be converted to positive, and b here is 3, so it will be 3 over s plus 2 square plus 3 square will be 9. So this will be the corresponding Laplace transform. A third question will be 1 minus the exponential of the multiplication of b sine plus d cosine. So if you look carefully, you will find this is a combination of multiple functions. So here we can try to split this combined function into simpler ones that each of them can follow this pattern. So let's take it one by one. The exponential one can be taken individually. Why? Because we mentioned from a while that we have a rule here called linearity, and the linearity here means if we have pluses and minuses, then we can take each part individually. So we will take one and take Laplace, and it will be 1 over s. Next, we have exponential multiplied by something. So we can take negative exponential multiplied by sine, this is the first, and another one will be negative exponential multiplied by cosine. And each of them will follow these patterns. So b sine multiplied by the exponential will be like that. So we will keep b as a constant here and use this pattern. Sine exponential. Exponential raised to negative at. So negative will be converted to positive, like here. And sine bt here is called sine ct. So we will replace each b here by c. So the final result will be c multiplied by b over s plus a square plus c square. What about the cosine? The cosine multiplied by a. So we have negative a. Here it will be positive. So here positive and here positive. Ct in a cosine. So we replace each b here by c. And a here will remain. So the final will be s plus a over s plus a square plus c square multiplied by d, which is a constant. All of that is combined with a negative sign here. Here is simple. You have a function, whether it's normal, easy, complex, long, short. You can simply try to find the patterns using the Laplace transform tables and the different properties. Now we need to know how to apply Python and MATLAB to solve the Laplace transforms. Go to script, lecture 7, lab exercise 1 Laplace. We imported some pi with different functions, sine, cosine, exponential symbols, and Laplace transform. Then we created the different symbols, t and s, and positive constants. In the first example, we defined, as we did from a while, in the first example, t multiplied by the exponential of negative 2t, and this would be f1 in the time domain. And to apply Laplace transform, we define the function, the time domain, and its domain, or the symbols. We will get the corresponding Laplace transform of f1. The same, we have exponential negative 2t multiplied by sine 3t. There's a function f2, and this will be the corresponding Laplace transform. Also, for the last one, we have 1, the exponential, the sine, the cosine, and this will be the corresponding Laplace transform. So simply, you write your function and use the function Laplace transform and pass to it 3 parameters. The first is the function in the time domain. The second is the t symbol and the s symbol, which refer to the time and s domains respectively. And this should be the corresponding output. And they are similar to what we did using hand calculations. The same for MATLAB. We defined the symbols, then we defined the functions, the first, the second, the third, and then used the function Laplace in MATLAB, also by passing 3 parameters, the function, the time domain, the t and s, which refer to the time and s domains respectively, and then printed each of them. and this should be the corresponding output for the MATLAB code. So it's easy. You define the function, use the Laplace function if you are using MATLAB, or Laplace transform if you are using Python, and get the output. Then you can validate the code output with your output to check if you are correct or not. The second part is called inverse Laplace transform. We mentioned that we need to solve initial value problems, IVP problems, and we are going to cover that after a while. One of the major steps in doing that is first to get the Laplace transform, then doing some processing, and then apply inverse Laplace transform. So we need to understand both of them, Laplace and inverse Laplace. So inverse Laplace transform will allow you to recover a time domain function from its Laplace transform. So the inverse of Laplace, which denoted by that symbol, of f of s will return or recover f of t. So Laplace inverse, this is the operator, and f of s, the Laplace transform of f of t. And this is essential for interpreting solutions found in the S domain back into real-world time behavior, such as track concentration over time or neural oscillation recovery after stimulation. And you can find that in many bioengineering models, such as cardiac pacemakers, track elimination, and muscle movement. So again, as we are going to cover, we will apply Laplace transform, then do something, and then inverse Laplace transform. And why we are doing that? Because we need to convert the differential equation into algebraic one and solve that algebraic equation and return it back to the time domain so it can be found easily. And there are many techniques to use to compute the Laplace transform, and you need to get familiar with each of these techniques. The first, which is common, called partial fraction decomposition, and this is used when f of s is rational, such as polynomial over polynomial, such as s plus 2 over s squared plus 2s plus 3. So you need to break it into known forms from the different tables. Table lookup, and we use that to identify the known patterns using standard Laplace transform tables. Convolution, and this will be applied for products of transforms. So if you have multiplication between f of s and g of s, and you need to get the inverse Laplace transform, this will be converted to convolution, f conv g of t. And if you remember, we cover that in the properties. Also, first second shifting theorem, and this is also commonly found, and this is useful when functions involve the exponential, which are called delays, or shifted terms like f of s minus a. And we are going to get familiar with these during solving the examples. So for the first example, 1 over s plus 2, it seems that this symbol. So simply we can look at the column called Laplace transform and check which one has this pattern. We can find that this one. So to convert it back, simply a here is 2 and it's plus, so we convert it back to negative. So the corresponding time domain f of t will be exponential of negative 2t. The second example, 3 over s squared plus 9. So let's check. Here is a constant, here is a constant, and there is s squared. When you find s squared here, then look to sine and cosine. So sine and cosine. We have a constant here and the square of the constant here. So simply we can say this looks like a sine because 3 square is 9. So we can rewrite that to 3 square. So it will look like that pattern. So the corresponding time domain f of t will be sine of at. A here is 3, so it will be sine 3t. Third example, b s plus d over s squared plus c squared. Simply, if you look to this column, you may say that we have vector, we have s, so it's a combination of sine and cosine. So simply you can convert that into simpler functions, decompose them. So we will split that into two parts. This will be the first part, ds over the denominator, and this will be the second part, d over s squared plus c squared. Why? Because this will follow the pattern of cosine, and this will follow the pattern of sine. How? This is a cosine. So we need s in the numerator, which is here, and s squared plus s squared in the denominator, which is here. So move that constant outside, like here, and this will be our cosine. A here is C, so it will be cosine CT. What about this one? We need in the numerator to find C. So as a trick, you can add C over C, because C over C is 1, so we didn't do any additions in the equation. What is the benefit? The benefit is now we can take this C over S squared plus C squared to convert it into sine CT. What about the rest? They are constants, so multiply by them. D over C, which will be like that. So simply try to manipulate the function to find some patterns to convert it back to the time domain. One more example, S plus 1 over S squared plus 4S plus 5. When you find something like that, then try first to apply partial fraction. If you couldn't apply partial fraction, or it's difficult, such as in our case, then you can simply think about the exponential multiplied by sine or the exponential multiplied by the cosine. How? Simply, we can put the numerator in this form or this form. If you took S squared plus 4S plus 5, then let's try to convert it to something square plus minus something. So the easy way here is to put S, because there is no factor here, constant, so it's S, and divide this by 2, so plus 2. What's the factor here? Simply put any remaining factors, which is 5. Also, return this back to this function and make both sides equal. How? S square, S multiplied by 2 will be 4. 2 square will be 4, so plus 4 should be here. So to make it equal, we will add also negative 4. So simply, we took that, and that in that factor, and the remaining is 5 minus 4. So 5 minus 4 will get 1. So the denominator will be converted to S plus 2 square plus 1. Double check again. S plus 2 square will be S square plus 4S plus 4 plus 1. So this will be 5. So it will equal to the denominator here. So we manipulated that original denominator into that. Now we can find that the numerator follows that pattern. And in the numerator, there is S plus 1. But we need in the numerator to be a constant or S minus plus. So simply, we will also manipulate the numerator to be on this form. How? We need S plus 2 in the numerator. So try to convert this into S plus 2. How? Simply add plus 2 and minus 2. So we didn't do anything, just plus 2 and minus 2. Then we will take S plus 2 as a factor here, so we can make it on the pattern of exponential cosine, and then the remaining would be 1 minus 2, which will be minus 1 here, and this should follow the pattern of exponential sine here. So now we have something plus something. Take the inverse Laplace for each of them individually. So the inverse Laplace of this part will follow the cosine, so it's exponential raised to the opposite of plus 2, it will be negative 2t, multiplied by cosine t, as the factor here is 1 and the square root of 1 is 1, so it will be cosine t. Here we have negative, put it here, the same exponential of negative 2t, because here positive 2, and it's 1, the square root of 1 is 1, so it's sine t. Take this as a common factor, it will be exponential of negative 2t multiplied by cosine minus sine. So it's simple. You have something like that. First, think about partial fraction. If it's not applicable, then try to convert that into a pattern that follows cosine or sine or both of them together. Now we need to apply code to get inverse Laplace transform. Good script, lecture 7, lab exercise 2 inverse. Import SymBy, symbols and inverse Laplace transform. Then define the different symbols, ES and constants. Define your examples. Then use the inverse Laplace transform. Pass the f of s to get f of t. And also here the symbol s, and t. If you remember, in Laplace transform we apply t and s, and here we're applying s and t. We need to convert from s to t. There's a second example, the third example, and the fourth example. We are using the same inverse Laplace transform, passing three parameters, f of s, and t. And for MATLAB, we did the same, but the function is called iLaplace, referring to inverse Laplace. We also define the functions, inverse Laplace, passing three parameters, f of s, and t samples, referring to the s and t domains, respectively. And this should be the corresponding output. Also, if you notice here, you will find that in each of them, you will find Heaviside function or unit step function. You can ignore it, as in the documentation, they mention that the unit step function is also known as the Heaviside step function, and we will see this function often in the inverse Laplace transforms, and this will be found in the output of Python code. So you'll find it here, 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 and all of them are 1, so you can ignore it. And this is the corresponding output of the MATLAB code. Now you can validate the outputs and the hand-calculated output. Now, after understanding how to apply Laplace and inverse Laplace transform, let's know how to engage both of them to solve the different initial value problems. So Laplace transforms are especially powerful tools for solving linear differential equations with initial conditions, as they will convert time domain differential equations into algebraic equations in the complex frequency domain, and this will make them easier to solve without integrating or guessing particular functions and solutions as we did earlier in the previous lectures. This method is widely used in bioengineering applications such as drug elimination, neural response in stimuli, and biomechanical systems with damping and external forces. There are 5 steps that can be used as a step-by-step process to solve the initial value problem using Laplace transform. First, take Laplace transform of both sides by applying Laplace to both sides of the ordinary differential equation and converting derivatives into algebraic expressions involving the S domain. The second step is to plug the initial conditions, and this can happen by replacing y dash naught, and y double dash naught, and so on with the given values from the problem. The third step is to solve algebraically for y of s, and this can happen by rearranging the resulting equation to isolate y of s, the Laplace transform of the unknown function y of t. The fourth step is to simplify y of s if necessary, and this can include using algebra, partial fractions, or other tools to express y of s in a form that appears in standard Laplace transform tables. So by the end, we need something like that. Y of s equals to something plus minus something, and so on. And these factors or parts should be on forms that appears in standard Laplace transform tables. Finally, step 5, apply inverse Laplace transform using non-inverse Laplace pairs or computational tools to return to the time domain and find y of t. To understand that, let's begin with this example. Let us consider a drug elimination model governed by this equation, and we have an initial condition like that. dc by dt plus kc equals r of t. And the initial condition is c of naught equals co, or c naught, where c of t is the drug concentration at time t, a is the elimination rate constant, r of t is the external infusion rate, or the forcing function, and CO or C naught is the initial drug concentration. So our case here is a constant infusion starting at t equals A. This means that there will be no infusion until we reach time A, and then the infusion will start. So before that, it will be 0. That's why R of t equals to R naught multiplied by the unit step t minus A. And this means that there is a delay. The unit step t minus a means that at time a, before that it's 0, and after that it's a value. So let's begin. The first step is to take and apply Laplace transform on both sides. There is the equation dc by dt plus kc equals r of t, and these are the different given values. So we are going to apply and substitute with these values in the original equation. We have k by 0.5, so it will be 0.5 multiplied by c. Rt equals r naught multiplied by the unit step of t minus 1, t minus a. So r naught equals 20, so it will be 20 multiplied by t minus 2 because a here equals 2. So this will be our equation. Let's apply Laplace transform. So dc by dt will be s multiplied c of s minus c of naught. And 0.5 multiplied by c will be 0.5 multiplied by c of s. And the Laplace of the nth step multiplied by 20 will be like that. First, we know that the Laplace of the unit step is 1 over s, and the Laplace of the unit step multiplied by a certain function will be the Laplace of this function multiplied by the exponential of negative as. So we need to use these two rules to find the corresponding Laplace of the right-hand side. So simply, 20 multiplied by the unit step of t minus 2 looks like this formula, where this function will be 1. So simply, we will extract the 20 outside, so it will be 20 multiplied by the Laplace of the unit step of t minus 2, and in this case, we will use this formula. We know that f of t minus a is 1, so the Laplace of 1, as mentioned here, is 1 over s, so 1 over s, multiplied by the exponential of negative as, which is here, and we will substitute for the value of a by the value of 2. And we have 20, so it will be here. So the final Laplace transform for the full equation, including the left and right hand sides, it will be s multiplied by c of s plus 0.5 c of s equals 20 multiplied by the exponential of negative 2s multiplied by 1 over s. Now we will plug in the initial conditions. We have c of naught, and c of naught here equals c naught, and c naught equals 0. So in this case, this part will be removed. So this will be simplified after plugging in the initial conditions. Now we need to simplify to get c of s on the left hand side and the remaining of the equation on the right hand side. So we will take c of s as a common factor. So it will be c of s multiplied by s plus 0.5, which is here, and is the right hand side. Now we can move this part to the right hand side, and instead of multiplication, it will be converted to division, like here. Now, we need to solve this algebraically. First, we will think about using partial fraction. If it's not applicable, we will try to find a way to handle the equation to be on the form of the exponential sign or the exponential cosine. So first, is it applicable to apply partial fraction? Yes, in this case. So we will apply partial fraction for the denominator. So this is the denominator, so it will be a over s plus b over s plus 0.5. Now we need to find the values of a and b. Simply multiply both of them. A multiplied by s plus 0.5 plus p multiplied by s equals 1. From that, let's get the coefficient of s raised to the power of 1, because it is the highest. So it will be a plus b, and there is nothing here, so it will equal 0. And let's get the coefficients of s raised to the power of 0. So it will be 0.5 multiplied by a plus nothing here equals 1 on the right hand side. So from here we will get a equals 2. Let's substitute by a equals 2 in that equation. We will get that p equals negative 2. Substitute, so we will have 2 over s minus 2 over s plus 0.5. Substitute in the original equation, so we have the numerator here, 2 multiplied by e of negative 2s, and there's the factors after the partial fraction. So here we extracted 2 multiplied by 20, it will be 40, and there's the remaining. Next, we need to apply inverse Laplace transform. So simply, we know these three formulas. The Laplace of the unit step is 1 over s, the Laplace of the exponential is 1 over s plus a, and the Laplace of the unit multiplied by a function. So we need to manipulate this to find a suitable formula so that we can inverse back the Laplace transform. So let's skip the constant for now and check that which formula or which rule that can get exponential multiplied by 1 over s. Simply, once you find exponential multiplied by f of s, then simply use this formula. So let's begin with this. Exponential multiplied by 1 over s. Simply, in this case, what you are going to do first is to get the inverse Laplace of the function, which is 1 over s, which will be the nth step of t. The next step is to apply the delay, which is converting each t to t minus a. So we have here a equals 2. So each t will be converted to t minus 2. So the inverse Laplace of this will be the nth step of t minus 2. Let's repeat it again with the exponential multiplied by 1 over s plus 0.5, which is here. Simply, let's focus first on the exponential. The exponential, which is here. So the inverse of it will be the exponential of negative a multiplied by t, like that, because a equals 0.5. Now, we need to replace each t by t minus a and ensure that it's multiplied by the unit step with the same t minus a. So here we will replace t by t minus 2. So it will be the exponential of negative 0.5 multiplied by t minus 2. And ensure that it's on this form. We have the function, but the unit step is missing. So we will add it unit step of t minus 2. Why? Because when you find the unit step on the function, it means that in its Laplace transform, you will find exponential, and it means that there is a delay. So simply get the function, apply the inverse Laplace of this function, then replace each t by t minus a, and ensure that it's multiplied by the unit step. Now combine all of that. This will be here, this will be here, and we have 40. Now factor the unit step of t minus 2, like that. So the remaining will be 1 minus the exponential. Now we have this final equation. You can simplify it more by simply converting this part to this part, but it's recommended to keep it on this form. So what is the meaning of this equation, or what is the interpretation behind this equation? Simply, the unit step here, or when you find something like that, this means that you have two parts. The first part is before the value of a, which is before the value of 2, and the second is after the value of 2. So before the value of 2, the value or the output will be 0. So the drug concentration will remain 0 until you reach t equals 2. And this is the meaning of the delay. There is a delay by a value of a. After that, the progress will start. So after t equals 2, the concentration increases exponentially and approaches to a maximum value. So it will start to increase until it reaches a maximum value. So what is the maximum value here? We can determine it. Simply, once you started by t more than 2 or equals 2, then you can ignore that part. Now substitute here. 40 multiplied by 1 minus something. And here it's infinity. So the exponential of negative infinity equals 0. So 40 multiplied by 1 minus 0 will be 40. So the maximum value that can be achieved or reached will be 40. So it will start at time equals 2 to increase until it reaches the value of 40, which is the value of the steady state. Now we need to know how to code that using Python and MATLAB. Go to script, lecture 7, lab exercise 3 drug. We imported different functions from SymPy. Then we define the different parameters such as k, c naught, a, and r naught. Then we define the symbols and function and r of t. And we use the step or the heaviside function as declared in our question, heaviside of t minus 2 or unit step of t minus 2 multiplied by r naught, which is 20. Then we got first the Laplace transform, or the first part, which is dc by dt. Then we got the second part, which is c. Then combined both of them in the left hand side. Then we got the right hand side also by using the Laplace transform. Now we have left hand side and right hand side. We will create the equation and solve that equation according to c of s. Now we got the Laplace of c of s. Substitute with the initial conditions, which is c naught equals c of naught equals c naught, which is here using the sub function. After that, apply inverse Laplace transform to get c of t. We can also plot that, create the time vector for plotting, let's say from 0 to 10 hours in steps of 0.1 hours. Then calculate the concentration by substituting by t or the time for each time point in the time vector in the CT, then start plotting it, create the figure, plot the time and the concentration, put the title, put X and Y labels, adjust the layout and add grid, save the figure and display it. Run the code. It will start to solve the initial value problem for the drug concentration, and after inversing the Laplace transform, it will start plotting it, and this should be the corresponding output or the plot. Before time equals 2, it's 0, and it increases until it reaches 40. And for MATLAB, we did the same. Defined symbols, defined the parameters, created dc by dt, created r of t, then we created the ordinary differential equation, then we applied Laplace on the ordinary differential equation with respect to t and s, the time and s domains, then we substituted in c of t with the symbol x, and we did this trick so that we can solve it later with the initial condition and apply inverse Laplace. So we are replacing this whole part that will be found in the output by just a symbol x. Then we substituted with the initial condition. Now we will solve according to the symbol x. After that, we will apply inverse Laplace, and this will be c of t. This should be our output for Python and the corresponding figure, and this should be the output of MATLAB. Now let's deal with another example that refers to modeling neural oscillations using second-order differential equations. And the problem statement says neurons in the brain can accept oscillatory behavior under certain conditions, such as during rhythmic brain activity or seizure-like patterns, and a simplified model of this phenomenon can be expressed as this equation: a second derivative plus 2 multiplied by the first derivative plus 5x equals 0. And we have these initial conditions. So we need to solve this differential equation using Laplace transformation. And it was noting that we now have different ways to solve differential equations, such as the ones we covered in the previous lectures, and also Laplace transform, including analytical and numerical solutions, and also Laplace transform. So let's begin with this problem. We have this problem and the initial conditions. So apply as a first step the Laplace transform on both sides. The right hand side is 0, so we'll keep it 0. The left hand side is the second derivative will be converted to that s square, because we can with 2, multiplied by x of s. Then we mentioned to decrease the power, so s of 1, s of 0, and x of naught, x dash of naught, plus 2 multiplied by dx by dt, which is the first derivative that will be converted to Laplace like that, to s x of s minus 2x of naught, plus 5x will be converted to 5x of s. Now, plug in the initial conditions. X of naught is 2, so replace each x naught with 2, and x dash of naught with negative 1, so replace this with negative 1. Now we have an equation, factor x of s, we will get s square plus 2s plus 5, like that. Then the remaining will be negative 2s, like here. Negative 1 will be positive 1. Negative 4 plus 1 is negative 3. So this will be our equation. Next, we need to get x of s and simplify it to be on the left hand side, and the remaining will be on the right hand side. So simply move that to the right hand side. It will be 2s plus 3, divide by that factor, then it should look like that. Again, if you have a polynomial or rational equation like that, a polynomial over polynomial, then we mentioned that we can use partial fraction. If it's not applicable, then we can manipulate that into a form that can be solved using exponential cosine or exponential sine. So if you try to solve it using partial fraction, it will be difficult. Then we will try to manipulate it on the form of exponential sine and cosine. So we mentioned the way. Take s square plus 2s plus 5 and try to convert it. Simply, s square will be s, divide that by 2, it will be 1, and ignore s, then power it. S square, it will be here, s multiplied by 1 multiplied by 2 will be 2s, and it should get another plus 1, because 1 power 2, it will be 1. So to make it equal, add or subtract 1. So this part will be converted like here, and 5 minus 1 will be 4. So the final denominator should be like that, s plus 1 square plus 4. Now we have x of s like that. We need to manipulate the numerator to be on this form. We have 2s plus 3, so we can split it into two parts, one for cosine and one for sine. The one for cosine needs plus 1 because we have s. So again, we will add plus 1 minus 1 in the numerator. Why? Because we can now take s plus 1 multiplied by 2 over the denominator as a part that be converted into cosine, and the remaining for sine. So 2 multiplied by minus 1, it will be negative 2, plus 3, it will be 1. So 1 over the denominator, it will be the second part, or sine. Now we have this. And we remember the inverse Laplace of cosine and sine, or the Laplace of cosine and sine. Both of them are equal. So this part, which is here, will be converted to cosine exponential. How? Let's check the value of a. It's plus 1, so it will be converted into minus 1. So it will be exponential of negative t. What about the cosine? Cosine p, which is here. So it was 4, so the square root of 4 is 2, so p equals 2, so it will be cosine 2t. So the inverse Laplace of this part will be 2 exponential of negative t multiplied by cosine 2t. What about this part? We need to multiply by 2 over 2 because we need to follow the pattern, as there was only one here. So what's next? We have 2 over the numerator. It will be exponential sign, like here. And the remaining is 1 over 2. It will be here. Now we converted the cosine and sine, or both parts together. By combining both of them in x of t, it will be that equation. Simplify, the final solution will be exponential of negative t multiplied by 2 cosine 2t plus 0.5 sine 2t. Now we need to script it. First, we imported SimPy with the corresponding functions. We defined the parameters. Then we created x of t and the symbols, created Laplace transform of x and dx and the second derivative of x. Then we created the left-hand side, as we did with the previous example, applied Laplace transform for the right-hand side, combined both of them together to get the equation, substituted with the initial conditions to get the Laplace transform. After applying the initial conditions, then we got the inverse Laplace transform, and this will be x of t. Also, you can plot it if you want, and this will be the corresponding MATLAB code. Also, we defined the symbols, we set up the parameters, created the differential equation, like here, and the right-hand side is 0. And if you have a right-hand side, you can put it here. Then we used Laplace to transform both sides of the equation and substituted. And remember, we substituted and replaced that by another symbol x so that it can be solved. Substituted with x and dx, then solved with the initial conditions. After that, we apply inverse Laplace transform to get x of t. And as an extra step, you can apply simplify to simplify the equation. And sometimes you may find that the output from that and the output from simplify are similar because there is nothing to simplify. After executing both codes, this will be the output of Python and this will be the output of MATLAB. And now you can see that the simplified and the non-simplified are similar, and both of them are equal to our retrieved equation, x of t. So in this lecture, we covered the Laplace transform and inverse Laplace transform, and we know that other than mentioned, we can use the tables for Laplace and inverse Laplace. If it's mentioned to follow the step by step, then we need to apply integral from 0 to infinity and apply the exponential of negative st. Then using both Laplace and inverse Laplace, we engaged both of them into solving ordinary differential equation or solving initial value problems by following a set of steps, applying Laplace, applying some processing such as solving for x of s, simplifying and substituting with the initial conditions, then returning back to x of t by inversing Laplace transform. And we covered two examples, one for drug concentration and another for modeling neural oscillations.